Hello and welcome once again to episode 36 of Code Completion. We are a group of iOS developers and educators hoping to share what we love most about development, Apple technology, and completing your code. My name is Dimitri and I'll be your host once again for this episode, and I'm joined today by my fellow completionist, Spencer.
Hey guys.
So before we get into our main topic, it's time for our Indie App Spotlight. First up is Event Zones by Bharat Kumar, an iPhone and iPad app that makes it really easy to set countdown timers and reminders for events that happen in different time zones. You can set up countdowns for vacation, anniversaries, concerts, or product releases, and Event Zones will translate that event's time zone and alert you when the countdown runs out. Event Zones is completely free to use, so please support Bharat by giving it a go and trying out their other apps. Finally, we have Orbit by Malin Sundberg, an iOS and Mac universal app for tracking time and preparing invoices. Orbit makes it really easy to keep track of how you spend your time, automatically catches when you've been idle, and will even show your running clock in a widget on your home screen or in the status bar of your Mac. When you are done tracking your time, Orbit makes it easy to get an overview of your time spent and create invoices to send to your clients. Orbit costs $7.99 per month or $79.99 per year for each member on your team, so if you do any sort of client work, please check it out to support Malin. Are you an indie developer? We want to hear from you. Please reach out to us on Twitter at Code Completion via DM so we can spotlight your app as well. So our main topic for today is all about computational complexity and overly clever code. So you've probably heard of this term before, so we figured it would be a good, this could be a good introduction for you to get to know it better. So Spencer, like myself, you did not really go and take a computer science based curriculum in your college years, and therefore you probably know as little as I do about computational complexity, or at least you didn't really pursue that as a educational career. In terms of like that, I feel like this is the most sciencey part of computer science, is like analyzing these sorts of things. So if you were to kind of describe what computational complexity is to someone like us who never really encountered it, how would you describe it?
Yeah, that's a good question. I'll try my best here. I'd probably say it's something like a way to calculate the amount of time that something will occur. So as an example, we have like like you call it big O notation, right? And so with that, you've got a bunch of different kind of notations. I don't know what you would call each different kind of thing, but you can kind of base, if I've got a loop of 100 things and I need to loop through it, that would be O of n, or in other words, it's sort of just like a straight. It would, if it takes 1 millisecond to run one iteration of the loop, it would take 100 milliseconds for the entire array. And then from there, you've got other notations that will sort of, depending on what you're doing, kind of let you break down the complexity and see how long, relatively speaking, whatever you're trying to do will take.
Yeah, so it
base complexity off of that.
Mm-hmm. It really is a counting game of seeing how long one given thing takes, and analyzing if that's going to become a problem if you do that one thing multiple times. So you brought up the big O notation, and the big O notation is some mathematical voodoo. If you're not like super into math, don't worry about it. It's not super useful to actually understand what is going on there. But we'll try our best to try to describe it in terms that do make sense. But I think you hit the crux of the issue. If you have a loop and you're doing the same thing over and over again, anyone can understand that if that thing takes a certain amount of time and you do it over and over and over again, then it's going to take a longer and longer amount of time. And it really depends on how many times you're going to be doing something. So if we were to really simplify what this is about, it's all about one work item, like what your computer is doing and how long that takes. Thankfully, nowadays, computers are really, really fast. If you want to add two numbers, that happens in literally under a billionth of a second. like very, very quickly, your computer will be able to add two numbers. So if you have a loop where you're adding numbers over and over and over again, even if it takes like 1,000 iterations of adding two numbers, you are never going to notice that amount of time pass.
Right.
So from the simplest like subunit of doing something, computers are very quick, and unless you're doing that a billion times, it's not going to take longer than a second. By like virtue of that one work item taking 1 billionth of a second. So generally speaking, you're not just adding numbers in a loop. That's not what we do when we make apps for the most part. We try to do more interesting things like looping through books in a catalog, or I'm running out of examples. To-dos in a to-do list, or
There you go.
tweets in a timeline.
Mm-hmm.
So we have model objects that we're kind of working on, and we want that model object to do something. So if you were to simplify that problem down, you have one work item, whatever you want your model object to do, and however long that takes, that would be considered O1. So the big O notation, like this is your introduction to it. Whatever that work item is, O1 is how long it takes for that work item to go from start to finish. Right. Now, if you do it 5 times, you're going to have O5. So if you tell your tweet to send and it takes however long it takes to send, and you do that 5 times in a row, I don't know why you do that with tweets, but let's think of it better. Yeah, you want to make a thread. So you have 5 tweets in a row.
Right.
They're all prepped. Everything is good to go, but it takes a certain amount of time for it to kind of register and be sent out. And it always takes the same amount of time. Let's simplify how this works. That would take O1. So if you do it 5 times in a row, that would take O5. If you do it 10 times in a row, that would be O10. If you do it n times in a row, that would be On. So that's where that On notation comes from. It just depends on how many times you're doing that one thing. So say you have a function called tweetThread, and that function will send out n amount of tweets. If you go ahead and do that, you know how complex that problem is. It's always going to take n times whatever sending a tweet is to actually send all those tweets out. And for the most part, that's probably not a problem. However, if you have a bunch of threads that you need to send out, all of a sudden you need to wait not only for that first thread to send everything, but for the next thread and the thread after that, and so on and so forth. And if you don't know how big these threads are, if they're different every time, or they can be as big as the user wants, then you're going to start to run into a problem, because now instead of having On, you're going to have On times n, basically, for the amount of threads. So n for the amount of tweets in one thread, and then m for the amount of threads. So very quickly, this gets more and more complex, and you can already see in your head how it's going to take longer and longer and longer to send out that final thread that's at the end of the list, because it really depends on how many tweets there are, and so on and so forth. So that's where this O notation comes from. It's trying to find, in general, and as general terms as possible, how complex the code that you're trying to write is, and simplify that down.
Right. Yeah, and just like Dimitri said, you can kind of see, even if you have 5 tweets and you have 5 threads, well, that's 5 times 5. You're, very quickly, exponentially grabbing or going, higher and higher with the amount of time you're going to take. And so, like Dimitri said, maybe you have some lunatic that's going to make 1,000 tweet thread, right? Then you're like, oh crap, okay, this could get really out of hand. And so one thing that we'll try to do is keep things as sort of flat as possible. So for example, maybe you have this example is like for thread in threads, and then in that for loop you have for tweet in tweets, and you send that tweet, right? Well, is there a way that you could do that differently? Well, maybe not in that case, but as an example, maybe after you send the tweet, then you have another for loop that says like for tweet and tweet dot, has been sent or something, and you do another for loop in that. well, is there a way that you could combine that work to say, well, instead of saying for tweet and tweet, send the tweet, and then for tweet and tweet, mark it as sent, could you just send the tweet and mark it as sent in the same loop, and therefore you are reducing that computational complexity? That's kind of the name of the game here, is to make it as simple as possible where possible. And I think that's something that may seem, I guess, like,
Obvious.
yeah, duh, of course you want to do that. But just in from my own experience and having looked over, we at Lambda School, we had sort of this interview at the end of or close to the end of their course, where they had to do some more computer sciencey technical question or whiteboarding, I guess, questions that had to deal a lot with time and space complexity, like we're kind of talking about here. And often, not oftentimes, I should say, but on occasion, I did see for loops kind of side by side that really could have been combined into one. And I get that it's a stressful environment, and so I'm not, faulting anyone for that. But it's something that if you're just kind of blazing through trying to write some code quickly and you're not really thinking about this, that's okay. At the very least, I would maybe go back through your code. And now that we're kind of talking about this, it would be easy for you to see, like, and evaluate, am I doing something like that where I'm making this overly complex and potentially making it run a lot longer than it needs to?
Mm-hmm. And this is a tricky sort of problem because you probably won't notice it in testing because you're testing with whatever data set that you're testing. But every additional item that you're adding to whatever you're doing has the opportunity of really running things slower and slower and slower. And every item that you add, the next one is going to be even slower than the previous one. So that's where it really comes to bite you. And as Spencer said, you want it to be as flat as possible. And that basically means you want it to be as constant as possible. So if we were to go through the tiers, you have constant time complexity, which means you're doing one thing and it always takes the same amount of time. It's constant. If you have a linear time complexity, it means that the amount of time will increase linearly with the amount of things that you're doing. And that's the ON situation, where you basically have a loop of constant things. If you have a loop of another loop, then you end up in the very iffy situation of being in quadratic time. Basically, you're doing every single thing that you add to what you need to do. Not only are you doing it, do you need to do the whole loop again? You need to do the loop of the loop again, and that's where things get hairy quickly. Remember, as Spencer said, if you have 5 tweets and 5 threads, that's 25. If you have 6 tweets and 6 threads, all of a sudden that's no longer 26, that's going to be 36. And that number gets larger and larger and larger very quickly. And it becomes very feasible to run out of time to basically do it. If you've ever sculpted an algorithm for yourself and it just seems that it's going to take forever, you just added 1 0 and then all of a sudden it's not really completing in any reasonable amount of time. And you wait and you wait and you wait. And then 4 hours later, it finally finished. Adding another 0 is not just going to add another 4 hours. It might add an entire lifetime to that problem. And that's where it gets very hard to kind of deal with writing programs. It's actually hard to find a way around that situation sometimes.
Right. A perfect example that I ran into one time was, I can't remember if I talked about this when I was teaching or if it was on the podcast, but I wrote just a kind of a fun app to take an image and sort it by its colors. So it would, rearrange everything, but it kind of made this nice gradient. And you could specify essentially what the output resolution wanted to be, and it would kind of chunk that into, if you wanted it to be 100 by 200 or whatever, it would kind of take it in chunks and it would be very quick. But as soon as you start getting into, well, I want this to be the same resolution as the image, and it's, multiple megapixels, then you're dealing with 3,000 by 4,000, and that, just like we talked about, 5 by 5 is 25 and 6 by 6 is 36. That's not a huge jump. But as soon as you start adding that 0 and making it from hundreds to thousands, it would just sit there and churn for 5-10 minutes while it was sorting things, and it's not a very efficient thing, and that's fine. But that's just one example that I have run into where it makes a huge difference, as far as it was looping through the x pixel and the y pixel. So I had that O of n squared, or O of n squared, that quadratic time, and it churned for a while. So definitely possible to do that in sort of a real world ish situation. Not really sure how often you'd be sorting images, but you can get up into arrays of the thousands and potentially be dealing with issues like this.
And I think the easiest problems of this come from misuse of APIs. For instance, if you want to see if an array contains something, you need to go through that entire array to see if it's in there. So if you only have 10 items in your little database that you're saving to a file, it might be fine to search 10 times through that. If you have 100 items, then it's going to take 10 times longer to search through that data set than the first one. If you have 1,000 items, then it's going to take 100 times longer than the first data set to go through that. So as your user is enthusiastically using your app, for instance, they are going to be adding more and more items to your app, so that way your app can collect and show it. And if you try to search, you don't want the experience to get slower and slower the more your user is using your app. But that's exactly what will happen if you naively just use array.contains, for instance, to see if that search term is in your array. And that's where different data structures really come to save you. One of them is a dictionary, for instance. So in a dictionary, if you want to find out if the dictionary contains something, it is much faster than an array at doing that. There's a specific term for this. It's called logarithmic time, because although a dictionary can get bigger and bigger, it's not going to make it slower and slower by the same amount every time you add 100 new things, 1,000 new things. You really have to add an exponentially larger amount of things to the dictionary for it to get linearly slower, and that's what a logarithm is. It's basically the inverse of an exponent. So logarithmic time, anytime you hear that term, that's excellent. Basically, that is the best scenario that you can be in, because it's basically constant for all intents and purposes. It will get slower as you add things, but it's not going to get linearly slower. It's just going to get a tiny bit slower for every 10, 100, 1,000, 10,000, 100,000 things that you add to it. You get like one notch slower every single jump you make. So dictionaries are great for that. Sets are also great for that. If you want to know if a set contains something, it will be able to tell you instantly if that set contains something, because it organizes its contents in a very different way. That said, dictionaries, sets, arrays, they all have their benefits and their weak points. And it's important to really see what data structure is going to work best for what you want to do, and to pay very close attention what methods you're using on that data structure, to see if that's going to impact you severely or not. And one thing that's pretty good about the Swift documentation is it will go ahead and tell you for these basic data structures what the complexity is for certain operations. And now that you know what that O notation really refers to, the closer you are to constant or logarithmic time, so O log n, O1, the better you are. If you happen to have a log on or an O n log n, those are also fine as long as you don't use them within loops. So there's all sorts of things to consider.
I've got nothing else. Sorry.
Totally fine. So basically what this comes down to is be very careful what methods you are calling within loops. Don't yourself put loops within loops. Try to keep everything as linear as possible. And anytime that you do have a method that is going to have to go and loop through everything, be sure to document that, so that way anyone calling that method, basically you in the future, remember not to call that method within a loop if you don't want to shoot yourself in the foot there. That said, time is not the only complexity that you can analyze with regard to all this. You can also have something called space complexity. And this comes down to how much space on your hard disk or how much memory you're using to perform a certain operation. So it's possible to make things linear in time complexity, but by being linear in time complexity, all of a sudden they're complex in space complexity. And this really comes down to when you're like writing sorting algorithms and really nitty gritty like reimplementations of stuff that is well solved. But for instance, if you have an array and you want to sort it, you can either use that same array to sort everything, or you can make a copy of that array and do the sorting in that copy. If your array only has 10 things, then your copy is only going to be 10 things large. But if your array has 10 billion things, 10 gigabytes of data, for instance, not an inconceivable number nowadays, then to sort that, if your algorithm needs to make a copy, it needs to now make a copy that's 10 billion entries large, and lo and behold, just that action takes a long time. It's not really easy to make that amount of memory just instantly available, even on modern systems, because oftentimes it's like sharing the entire space, all your terabytes, with everything. So you can get smaller chunks very easily, but that big giant chunk has to start moving stuff around and making that available. And that can really get to you as well if you're not careful. So if you can make sure that whatever operation you are doing can be done in place in the same amount of memory, and you're not making copies all over the place, that is also going to be to your benefit. Basically, every copy is an ON operation that you need to be aware of.
So that goes back to that example of pixel sorting. That was the other thing, was I was then sorting that array of, 12 million elements, essentially, if it was like a 12 megapixel image. So what you're saying is if you use .sort, or sorry, let's see. Yeah, sort is the one that sorts in place. Over sorted, then that is a better outcome.
Yes, especially if you already have a mutable array that you have, that is going to be much faster than sorted, because sorted needs to go and make you a new copy of that array just to give you something different than what you started with. And the bigger that image, if it's a 100 by 100, that might go fast. That's only 10,000. Am I doing that right? Yeah, 10,000 elements. Just add the zeros.
Yeah, right.
But if it's a 200 by 200, all of a sudden that's much larger than 10,000. It's not 20,000. It's 40,000.
Right.
So it gets much larger and larger the bigger your image is. Even though you think, oh, I'm just increasing it linearly, it's increasing exponentially because you have 2 dimensions to it. If you have 3 dimensions to it, a loop and a loop and a loop, that can get even hairier. So it's something that you need to be conscious of whenever you're writing code, especially whenever you're writing an algorithm. And it might come up in the most surprising ways. You just wanted to save your data to a JSON file to save it to disk. Every time the user adds an entry to your app, guess what? It needs to rewrite that entire file. If you have 100 things, that's one thing. If you have 101, it's going to take ever so slightly longer than it took for the 100. As the user adds more and more stuff, it's going to get slower and slower and slower to save stuff. But one thing that you should definitely keep in mind is if your data set is never going to be growing in size, it's going to be relatively constant in size, then it's not a problem. You really don't need to worry about those situations. It can be n to the power of 7 if there's only 5, if n equals 5. It's not an inconceivable number at that point. You are sure that it's always going to happen in the same amount of time. So always think about what the problem space is and if things are going to get larger or smaller over time.
Yeah, and I think with that, one of the questions you should ask yourself is this going to be something that can be increased, the amount of things can be increased by the user, like tweets, right? You'd probably only have maybe, I've seen threads of maybe like 50 or so tweets at once, and I'm not sure they wrote them all out at once like you can kind of queue them up. But, in theory, there could be that one lunatic that does write 1,000 tweets at once, just with one letter each or something. But if it's having to perform that URL session request every time, then you could get yourself into a situation where it could have an issue with its time complexity. So user facing stuff, definitely be careful with.
And that goes
I've
for
heard. Oh, go for it.
and that goes for things that you're showing on screen too. If you're showing one thing on screen at a time, that's gonna be fine. If you show 10 things, probably gonna be fine as well. 100 things, all of a sudden the system is not prepared for that, and it starts to struggle, especially in older devices. So always think about how much you're putting on screen, especially from a user interface point of view, because these complexities, they carry over throughout the entire system. I would say the best way to kind of gauge like if you're doing this right or wrong, because there's lots of different scenarios where we just told you watch out for this, except in this scenario don't worry about it.
Right.
So when do you know if you're doing it right or wrong? So I think the best thing to do is to measure it, honestly. So instruments is a great tool, and that can help you profile and see, are there any slowdowns in your app. Go ahead and test it with 10 more items.
Right. You're talking about like with like the time profiler. Instruments are really cool if you've never used them. There's a bunch of the instruments that I haven't used, but the two that I've used the most probably have to do the most with what we're talking about here, which is the time profiler, and I think it's just called the memory profiler or allocations. Like, no, that's different. But the time profiler is really cool because it will let you record the usage of your app, and let you even, like, let's say you've got you're making those 5 tweets, right? You go through the simulator, you're composing those tweets, you kind of queue it up, and you hit tweet all or whatever. The cool part about that is it's going to measure everything kind of during that whole time. But then when you're like, well, I really only care about looking at the time after I hit, tweet, and kind of everything that was running from the time I hit tweet to the time it says the tweets are sent or whatever, you can kind of filter that down and look through this call stack, and it will show you essentially command by command how long it spent on whatever was being executed. So if you've got again maybe a loop in a loop, and it's sitting there waiting for those methods or those completion closures to finish, it would say, yeah, that took 6.5 seconds or whatever. And so you can kind of see in what place you are spending the most time, which can be super helpful.
Yeah, and the best way to visualize that is via a graph. It basically paints the graph very, very blue the more it's doing in that time. So this is where I should pay attention, right at this chunk of time. And you don't even need to remember when you tap send. You know that's causing that right there, and that you can go ahead and take a look at exactly what methods are being called, and likely you have a method that is implementing a loop, calling other methods, and you might think, oh, that's fine. But then if you dive down into the methods that are being called by the loop, those themselves have loops, and that's when it gets slower and slower, especially as you add more data. So while you're testing, always make sure, add more data than you think the user will ever need. If your app can survive that, then it's fine for anything that the user might do. But if it can't survive that, then you really should rethink how to architect what you're building, because it will likely run into problems later on the more your users use that functionality. The second thing that you can do is benchmark. So one thing I loved about NSLog that has kind of gone with print is it would print out the time that log statement kind of came out at. And that is super useful for quick and dirty benchmarks. So if you want to know how long something takes, you can you can NSLog start, you can NSLog stop. And then when you look at the console, you'll see 2 times, and you can kind of just do the back of the napkin calculation to see how long that took. If you are now working, instead of on 10 items, on 100 items, you can go ahead and see, was that 10 times slower? Was it 100 times slower? Was it 2 times slower? And that can give you a good idea of how things are being handled by a little small part of your code without you needing to test with 100,000 things. You can just kind of graph out with a few data points how things are progressing. So one last thing that I wanted to bring up, and that is while you're doing all this, it's possible for your algorithms to kind of get very complicated and very fine-tuned as you're kind of eking out performance left and right. Maybe you're leaving old code in place as you're rewriting, and the original intention of your code can very easily get lost. So one thing that I would highly recommend to everyone that is kind of jumping into code that you need to fix in some way because of this is to document a lot, especially as you try to make things clever. It's very important that you document that process so that way it's possible for future you, more than anyone else, to be able to discern and interpret what exactly is going on, because the computer will just follow those instructions step by step. And if there's a bug in there, it's going to happily fall in that hole every single time. But you're not necessarily going to notice that if you are coming back to it months later and you don't really know what every line of code is really doing, especially as you're adding or subtracting like small amounts to make sure that everything can be very optimized, working in a window that's sliding across an array and things like that. It gets very easy to kind of get lost in code like that, especially if like doing one line of code differently would create a copy and cause all sorts of things to kind of balloon from that point of view. So if you're playing with like very nitty-gritty solutions to things, always document that code. And the reason I bring that up is because it's possible to eke out even more performance out of what you're doing by studying how the CPU is caching like various variables. Where you define those variables are going to generate different instructions, and being beholden to how your code gets changed into instructions for the CPU can inadvertently set you up for failure in the future as things get changed slightly differently, especially if your code is not readable. So as much as possible, try to keep your code readable. It will improve in speed in the future as compilers evolve. But if your code is not readable, then it's just going to collect dust as time goes on. So do be very careful about that.
Yeah, I think that's a huge thing with making your code more legible than being, for example, concise or like performance aside. I think it's a huge benefit, like you said, mostly to yourself when you're coming back to this a few months later, whatever it is, to be able to look at it and know what's going on. And sometimes you've got code that it may be complex enough for you to not understand it just by reading it. And that's where, like Dimitri said, that documentation comes in handy. For me, I'll notice that it's harder for me to write documentation because I'm like, no, I've got this. I understand this. But it's like, of course I do. I just wrote this code. I'm not really thinking about myself in the future and how hard it could be for me to sort of relearn whatever I'm trying to or whatever I'm, currently working on a few months later. Who knows where, what I'll have done in the next few months. I could be working on a completely separate part of the app by then and haven't touched this. Like you said, it's just collecting dust for the last few months. Maybe you haven't touched it since then. Documentation is huge, and it really doesn't take that long. And, we could all get better at, like we always say, documentation-driven development, because it's a small amount of time that you spend in the present to save yourself a lot of time of having to, at the very least, kind of read through that code and try to figure out what's going on. If not, go look at other tutorials and figure out, like, what was I even doing at that time.
Yeah, it's important to explain why you made a certain decision, not what the code is doing. It's clear to see what the code is doing. It's calling this method. Why is it calling that method? That's where you want to explain yourself. Why are you choosing to do it in a certain order? Why are you choosing to use one method over a different method? All of those explanations, especially if you just went through an intense debugging session to really figure out what the optimal path was, by logging your thoughts and making sure that your intentions kind of carry through, that's going to do a lot more than seeing the change in Git where you saw the previous version, then you see everything
Yep.
changed and here's a new version. You're not really going to get that step-by-step process of why you went from the old version to the new version and what benefits each change made. And from that point, it's kind of easy to just throw something out and rewrite something and be like, this seems better, but really try to think about why it's better, and to log that down. Even if you're not sure, say, I think this is doing better because of this, and this. When you have more experience in 6 months and you look back at that, you're like, I don't think that's the reason. You've actually introduced 3 bugs here. You passed yourself. So let's go ahead and use these same intentions that are logged, and rewrite those portions so that way they don't have those bugs. So that is something that takes skill to kind of develop and nurture, and to know what to write for what kind of documentation. But generally speaking, you will get better at doing that the more you document. And especially starting off, you're probably not going to be writing super complex code. But as you gain more and more experience, you're going to start dipping your toes into, oh, look how clever I am. I made this 200-line function down to 18 lines,
Right.
and it's super efficient. And all my variables are named A, B, C, D, E, F, G. And that's, you might think, oh, this looks super neat. I made a drawing out of my code at the same time. That is useful from an academic point of view, but not useful
Right.
from a maintenance point of view. So enjoy the fact that your like Xcode, what we all use for iOS development, will autocomplete everything for you. So use long variable names. Don't try to shorten things up. And make sure that whatever algorithm you're concocting is really optimized to be legible first and performance second, always. Even if you think that you can eke out extra performance, you can make it more legible by adding words, generally speaking. And that will help you in the long run.
Yeah. There's the famous saying that premature optimization is the root of all evil, right? Mm-hmm. Don't try to write absolute perfect code the first time, because you probably won't. And like Dimitri said earlier, we've got computers in our pockets that are blazingly fast, that most of the time you don't really have to worry about performance for a lot of cases, unless you are getting into some gnarly time complexity. But I think that's more of an edge case than we may make it out to be right now. But writing cleaner, better, more simple code is, I think, in many ways preferable. I would always tell my students to not write like those one-liners where you're doing like dot filter, dot sorted, dot whatever, reduce all in one line. Just write it out. There's nothing wrong with it being 10, 15 lines of code if you can read it faster and you can understand and grasp what's going on a lot more quickly. And then if you do have performance issues, again, like we said, run the time profiler or whatever you need to, benchmark it and see where you can fix it. But you're going to spend so much time trying to write perfect code that you'll never write any code at all. So just get something down and then come back to it if you need to.
Yeah, and it's funny that you bring up that specific example where you say dot filter, dot sort, dot this, dot that. Those will actually make copies at every single instance in time. So the more of those you add, the more complex you're making the code. It doesn't really stack very well. And there are variations on those that do it lazily, which lets you set up a chain of commands, basically, but they're only going to be run at the very last moment, and that's going to save you on memory complexity specifically. So even with that specific example, yes, your code might look better, but unless you know how to use those well, basically use lazy and only judiciously, then you're going to make bad code in that moment. That said, might not be a problem. Right. Everything might be fine by having that code, it might be more legible to spell those things out rather than write your own for loop that does everything yourself and is super complicated. So it's important to test. It's important to document. And I would say like one final like gotcha that you should pay attention to is sometimes it's not easy to rewrite the code in a certain way. Kind of the famous examples of this are recursive functions versus iterative loops, for instance. So it's very easy to recursively think about a problem. It's like, okay, I'll do this. And then with the subset of information, I can call that again. And then that can call itself again, and so on and so forth. And that might be fine for some scenarios. Like time complexity wise, that might be a perfectly linear algorithm if those are your constraints that you need. But what you're slowly going to be doing is eating into memory every single iteration. So if you need to do that 100 times, that might be fine. If you need to do it 10,000 times, even if it completes within just a few seconds to get what you need done, and you show a loading bar or whatever you need to do, that might actually run out of memory just from you calling methods or closures one after another. And that's because every time you call a method, it saves a little piece of memory to save where you are in that method on something called the stack. And before that, if that method finishes, it cleans itself up. But if it calls another method before it finishes, it adds that stack and adds that stack. And you slowly eat up more and more memory. Now, most of these algorithms, it's possible to rewrite them iteratively, and that is to say as a loop. But all of a sudden, the code is no longer comprehensible. So it's very tempting to kind of get lost in the weeds trying to do that. It's a fun exercise for some. It's like a puzzle. It's like you have this problem expressed this way. Can you express it any other way? But it is something to be careful of, especially for something that happens a variable amount of times. If you know it's only going to happen 5 times, and if you add another 100 things, it might only happen 6 times, then it's not an issue. But if for every new thing that you add one new entry to that stack because you've been calling that method one extra time, that can lead to problems. So although like what each version of the algorithm is trying to do is the same, in the end they're all fruit, you need to go ahead and be very careful about how you build out your algorithm, and if you're calling a method over and over and over again, that is something to be careful of.
I think kind of to really sum everything up from my perspective is, again, from my perspective here, Dimitri may have a very, very different perspective on this, but on my day-to-day, I don't generally worry about time and space complexity because I'm not doing anything that merits needing to loop in a loop in a loop. And so I just don't worry about it. It's in the back of my head and thinking, ooh, if I do start running into a loop and a loop and a loop, or I do see memory usage spike, then I can say, all right, let's go ahead and profile this, or let's, think of a better way to do this. But I wouldn't necessarily concern yourself and freak out with every single line of code you're writing. Think about what is the time and space complexity of this, because it's probably not going to matter in 99% of the cases. So don't let us, having an entire episode on time and space complexity make you think, oh crap, this is something I absolutely need to be watching out for every single moment that I'm coding. Just have it in the back of your mind and know that it exists and know how it works so that you can solve any problems that do potentially come up, and you can recognize them if you do end up introducing them or someone else does.
And in the show notes for this episode, we'll add a few links that you can go ahead and read up more on these topics if you do want to brush up on them. But as Spencer said, for the most part, you're not doing science work. You're just writing an app. And that's a completely separate set of skills for the most part than inventing new algorithms. And unless you enjoy coming up with new and interesting algorithms, you don't necessarily need to worry too much about much or all of this, if at all. So do take it at your own pace. Do keep in mind that some things can be made faster if you wanted to really hunker down and speed it up, but always measure first so that you can find out if it's worth it.
Hmm.
Sometimes it always has to be worth it because you're running under battery constraints and things like that. But for the most part, it doesn't necessarily always need to be, especially for apps. This week's episode of Code Completion is brought to you by Not Pho. Tired of eating the same old meals time and time again? Consider Vietnamese food. You might already know of pho, but there are a ton of other flavors specific to Vietnamese cuisine that are sadly not well known around the world. This includes everything from sandwiches like banh mi, rice plates like com tam, and even the deliciously savory crepes known as banh xeo. That's where this app, Not Pho, comes in. It's a free to try app dedicated to teaching you more about the wonders behind Vietnamese cuisine, brought to life with colorful and interactive illustrations and animations. Learn how to make many classic Vietnamese flavors at home, but even if you don't cook, you'll know how to order like a pro the next time you visit your local Vietnamese restaurant. New since version 1.1 is the Chef Club, regularly bringing you even more recipes like avocado and mango smoothies, fried rice, chicken curry, and my personal favorite, chicken beef, for the low cost of $2 a month with more recipes added regularly. Thanks again to Not Pho for sponsoring our show. Search for Not Pho, that's Not space PHO, on the App Store today to give it a try, completely for free. Now that we've gone through our topics, it's time for Complete the Code, where we quiz our listeners on your knowledge of Swift, Apple, and all things development. Here's last week's prompt once again. Spencer?
Yep. So it is a key command related question. If you're listening to the podcast, check the podcast art or the show notes in order to follow along. So the prompt here is we have some code that sets up a label, but in doing that we misspelled our label. Which key command in Xcode will allow you to rename the variable that you've selected everywhere that it appears in the current scope?
So, super useful key command. Can you
Mm-hmm.
complete the code? Tweet your answer to us with hashtag complete the code, all one word. The first to get it right will get a shout out on our next week's show. So, as always, I want to personally thank everyone for listening in this week. Be sure to follow us on Twitter at Code Completion to know when new episodes get released, and feel free to tweet at us if there is a topic you'd like for us to dig into. Most importantly, as a small podcast, please be sure to share with your friends and family who are also interested in any part of the process of app development. It's your support that enables us to continue doing this, and we hope to grow a healthy community around everything we discuss. Once again, I want to give my thanks to Spencer, who is at Spencer C. Curtis, that's SpencerCurtis, on Twitter for joining me this week. My name, once again, is Dimitri. You can find me at Dimitri Buniol, that's DimitriBouniol, and we'll see you all next week.
Bye.
Bye. Yeah, I think this bit me once, like dealing with the time complexity stuff. When I was trying to find out if I should show annotations for a certain time range within video, like while you're playing back that video and the playhead is moving, to find
Mm-hmm.
out if you're within a time range, because there's no like
Oh,
preset data structure that's like, oh, here are your time ranges and you can just look them up in a dictionary or anything. So I needed to have a very interesting algorithm that I came up with that keeps track of like where the user is, so that way it can quickly index to that specific time ranges that can overlap and all that. And that was a pain. So
yeah.
my heart goes out to everyone who needs to implement subtitles, because subtitles are time ranges essentially,
Right.
and that feels like it's complicated because it's not linear. The amount of data that you have, you can't just jump to index uh, 5,000 frame 5,000 and know what subtitle to put.
Yeah. CM times are weird. I don't know if that's what you were using, but we use a lot of CM time,
Mm-hmm.
and it's just like, what is this? It's yeah,
Well,
it's
it's made to
bizarre.
be absolute, right?
No, I know, I get it, but it's just like this is like when my boss kind of when I started working there, he's like, you might want to look into CM time and how it works and everything if you're not familiar and stuff. I was like, okay, and I was like, it's just I don't think it'll be that bad. And I looked into it, and I was like, this is way weird. Like it's not terrible, but it, there's like four things that have to do with the way that the time works and everything is like
Mm-hmm.
this is not straightforward, I guess,
Mm-hmm. Well, it's all
at first
because
glance.
decimals are not accurate, right? You can't have a third of something like directly represented, but with a CMTime, you can
Right.
have that perfectly represented.
Yeah.
And that's because it's basically because audio and video does not match. And that's a wonderful quirk of everything.
Yeah.
Yay to frame rates like 23.98, I think it is.
Oh, yeah.
Which is actually 24 divided by 1001,
Yeah.
or 2400 divided by 1001. And that's because audio is at a certain frequency and video is at a different frequency. And that is the common divisor.
Yeah.
So, yay for CM times.